in previous lectures we developed the theoretical foundation of antennas. Specifically, we investigated characteristics of a basic current element, what is called the Hertz dipole, and then using the information which we got from the Hertz dipole, we analyze the radiation characteristics of a dipole. And then we saw as the length of the dipole varies, the radiation pattern, which is one of the crucial characteristics of an antenna, it varies, and depending upon the length of the antenna, you have what is called multiple lobes or multiple beams, that means multiple directions in which the radiation goes. We also saw that as the length of the antenna increases, then there are certain directions in which there is no radiation apart from the principal nulls which are along the dipole. There are some other directions also in which there is no radiation or there is no electric and magnetic field. Then we can say that if you have a general antenna has a direction in which the maximum power goes, then there are certain directions in which no power goes, and there may be some other directions in which again you are having a local maxima, that means if you go in the neighborhood of that direction the power is maximum in that direction, but it is not the absolute maximum if you see the three dimensional space as a whole. So today we will try to investigate the general characteristics of an antenna, which will be also applicable to the Hertz dipole and the linear dipole, but here we will essentially try to characterize the radiation patterns of an antenna. This is important because when we have different kinds of antennas, normally we require some comparison mechanism, that means a mechanism by which the two different antennas can be compared. At the moment we have a radiation pattern which is a very elaborate description, which is a three dimensional surface, and it is very difficult to really compare one antenna with respect to other quantitatively. Looking at the radiation pattern, we can always say this antenna has certain direction for maximum radiation or certain directions for nulls, but what we are looking for is some quantitative measure on the basis of which the antennas can be compared. And that is what essentially we discuss in today's lecture. We discuss what is called the general radiation characteristics of an antenna. So let us look how the general radiation pattern would look like. So as we saw, the radiation pattern is a variation of the electric field magnitude as a function of theta phi. Let us say if I take any plane, then the radiation pattern in general would look something like that. Here I have drawn the magnitude of electric field as a function of angle, and this angle I am measuring in the plane of the paper. So this is the direction in which you have a maximum electric field, that means you get maximum power. Then there are these directions in which there is no electric field, so no power goes in this, and as we saw earlier for the dipole we call these directions as the nulls. So we have null here, we have null here, we have null here, here and here. So in this particular radiation pattern we have the direction in which maximum power goes, and then we have got these 5 directions in which no power goes. The electric field is 0 in these directions. Then if I go in this direction between these two nulls where the electric field is locally maximum, so if I measure the magnetic field, the magnitude of the electric field here, it is higher compared to the neighboring points, same is here, same is here, same is here. But this maximum amplitude is much smaller compared to this amplitude, which is really the absolute maximum which you see in the radiation pattern. So this direction in which there is the absolute maximum, we call that as the main beam of your radiation pattern or main beam of the antenna. So we call this lobe or this angular region, where the maximum power is going as the main beam of the antenna. And then all these minor lobes which you are seeing, the angular zones in which the power goes, again there is a local maximum, but this is much smaller compared to this. All these lobes are called the side lobes of the radiation pattern. So, all these small ones are called the side lobes of the radiation pattern. So, in this case we have 1, 2, 3, 4 side lobes, and we have one direction of the what is called the main beam. Now, as we saw last time, that depending upon the application, you may require a very directional antenna, in the sense I want to send the power only in a particular direction, as we saw in case of, let us say, microwave tower. So, in that case I want these quantities, the side lobe should be as small as possible, and most of the field must get concentrated only in the direction of the main beam or the maximum power direction. Whereas, if I want to use the antenna for broadcasting application, then this beam should be as wide as possible, and there should not be these zones where the nulls are there. So, I have now, depending upon the application, variety of requirements for radiation pattern. In some case I will require narrow beam, in other case I might require a very wide beam and no nulls, because in broadcasting applications the nulls are not desirable, because in those sectors there will not be any radiation and there will not be any reception of the electromagnetic wave. The same radiation pattern many times is drawn in a Cartesian way. That means, if I measure the angle and plot this angle like a Cartesian coordinate theta. So, this angle, let us say this was some reference direction which I had from here, and I measure all my angles like that as theta. I can plot now from theta, which is theta equal to 0, which I have taken some reference direction, this is 0. The maximum beam will be in direction maybe some 30-40 degrees. Then you are having a null which is somewhere around 0, then you are having a side lobe. So, the pattern might look something like that. And so on, where this thing corresponds to the main beam of your antenna, this null would correspond to this null would correspond to this null would correspond to that. So, if I say this is null 1, this is null 2, this is null 3, this is null 4, and this is null 5, this is the main beam, and let us say this angle of the direction of the main beam is denoted by theta naught. So, this angle, this will be theta naught, then this will be null phi. So, this direction is phi, this direction will be null 1, this one, this will be null 2, this will be null 4, and so on. So, essentially we can take the radiation pattern, which is actually a polar plot in a plane, as a Cartesian plot, where the angle is plotted on the x axis and the amplitude of the electric field is plotted on the y axis. So, this is you are plotting here mod of E. Both type of patterns are seen in literature. Some people prefer to draw the radiation patterns like this. Sometime when you want to do more calculations, maybe drawing the radiation pattern like this comes out to be more handy. So, now if I look at this radiation pattern, there are certain characteristics parameters I can extract from this radiation pattern, and the first thing immediately comes to your mind is the direction of the main beam. So, different antennas can be sort of compared on the basis of direction of their main beam. So, we have a parameter, the direction of the main beam. theta naught. So, normally when we compare the radiation patterns, we define certain reference direction, and with respect to reference direction, essentially we give the direction of the maximum radiation. Here I have written theta naught, but in general if you see in the 3 dimensional, this will be theta naught phi naught, because it will be, this beam will be even inclined in the phi plane. So, in general you can say direction of the main beam is given by theta naught phi naught in the angular coordinates. The second thing which you can see from this radiation pattern, and that is what is the angular sector over which effectively the beam is illuminating the region. So, there are various possibilities. One is, I may say if I go to the nulls, the radiation goes to 0. So, effectively I have a angular sector which is decided by these 2 nulls over which the power is going in the main beam. But then we will note that when I go very far away from the main beam, go towards the null, we are having a variation of electric field from maximum to 0 over this sector. Normally in electrical engineering we define a quantity what is called the effective width. That means that is the region over which the power lies within 50% of its maximum value. Since power density is proportional to the square of the electric field, and this is the plot of the electric field, the electric field, if it lies within 1 over root 2 of its maximum value, the power will lie within 50% of its maximum value. So, what we do, we can define the 2 directions where the electric field drops to 1 over root 2 of its maximum value. So, let us say since the radiation pattern is normalized, this value is 1. So, this value is 1. Then I go to these 2 angles, one here and here, which correspond to these 2 angles, where the electric field is dropped to 1 upon root 2. So, I have got these 2 directions, let us say theta 1 and theta 2 on either side of the maximum of the main beam, where the electric field would drop to 1 over root 2 of its maximum value. These things then we call as the 3 dB points on the radiation pattern, because these at these points the radiation or the power density would drop to 50% of its maximum value. So, then one can say if 50% variation of the power density is acceptable, we can say effectively that is the angular sector over which your antenna beam is illuminating the region. The power is going effectively over this sector. So, we define this beam width theta 1 minus theta 2 as what is called the half power beam width of the antenna, and that is the effective width over which the antenna is sending power along the main beam. So, we have a second parameter what is called half power beam width. Again, we can define now half power beam widths in various planes, because this region which you are considering, it may not be a circular kind of region. So, it may not be illuminating an angular sector which is circular. It might have in general an arbitrary shape. So, in general this half power width will depend upon the direction. So, if I take this direction of maximum radiation and if I take different planes passing through this quantity, the half power angle, that would be varying. However, as we saw earlier that a radiation pattern normally is taken like a 2-dimensional figure by taking the sections of a 3-dimensional actual radiation pattern, and these 2 radiation patterns we called as the E and H plane radiation patterns. Same thing we can do for general radiation pattern also. So, we can say that 3-dimensional radiation pattern whatever we had, we take 2 sections, one by plane which contains the electric field vector, another which contains the magnetic field vector, and if I take these two sections, I will get the half power beam width from the two planar radiation pattern which I get by sectioning the 3-dimensional radiation pattern. So, I can get this half power beam width in these two principal planes, E plane and H plane. So, I get the radiation pattern, from there I get the half power beam width, which could be written now as theta half power theta HP, and this could be in two planes. So, I can call this as the E plane half power beam width or H plane half power beam width. So, I can say that this half power beam width is half power beam width E plane and half power beam width H plane. So, this is a very important parameter, because what this tells me is the effective angular zone in which the power will be radiated by the antenna. And later on we will see, essentially we make an approximation that within this region the field we assume practically constant, though there is a variation of 1 over root 2, and we assume that beyond this the field is suddenly dying down 0. So, this is the effective width over which the antenna radiates the energy. So, this is one of the very important parameters. As we mentioned, this half power beam width, many times it is also called as 3 dB bandwidth, 3 dB beam width. Because that is the angular zone over which the power variation will be 50%, that is 3 dB. Then we have the third characteristic of the radiation pattern, and that is, if I say what is the effective angle over which the radiation goes, though I may accept a variation, but the field should not be 0 within that region. So, I may go as far as these nulls, and then I can define the beam width between the first nulls. That means, if I go from the direction of maximum radiation to the first null on this side and the first null on the other side, this beam width from here to here, that we will call as the beam width between the first nulls. So, this beam width we have here, this is theta half power, and the beam width which we have from here to here is theta first nulls. So, we have the third characteristic parameter, that is beam width between first nulls. We call that BWFN. This quantity is not very reliable quantity, in the sense it does not really give you the correct description of the zone over which effective power is going. There are many antennas for which the beam width between the first nulls remains same, but the half power beam width keeps changing. So, basically the half power beam width, that is much more reliable parameter as far as antenna description is concerned than the beam width between the first nulls. But if you take a general antenna like an antenna array or a uniform current distribution or something, these two are closely related. So, theta between first nulls and the half power beam width, they will be closely related to each other. The next thing which is characteristic of the radiation pattern is that you have a main beam, that means that is the direction in which the maximum radiation goes. So, the antenna is designed to take the power in that direction. We also have seen that this power will go into a finite area, which will be decided by what is called the half power beam width. So, that is also acceptable, that this antenna is going to illuminate certain region around the direction of the maximum radiation. However, we did not have any intention of putting power in these directions. The antenna is designed to give power only in that direction. But as we saw in case of even dipole or in general, there will be always a direction between the two nulls where there will be a small amplitude of electric field, that means the power will leak out from the direction which are the side lobes. So if you are designing an antenna which is very directive antenna, what that means is the antenna is designed to really focus power in a particular direction. There will be always some leakage of power in the directions of the side lobes. So the side lobes as such are very undesirable feature of the radiation pattern, and that is why in practice we try to minimize the amplitude of the side lobes. So smaller the side lobes, better the antenna, because it gives you the less leakage of power in the unwanted directions. So this measures that how much power is going to leak, or what is the amplitude of the side lobe with respect to the main lobe, is a parameter which is a figure of merit for a good directional antenna. So the ratio of this to this. Now the side lobes need not be monotonically decreasing as we go from the maximum direction. Maybe this side lobe will be lesser, this will be more, is possible. So what we do is we just find out the highest level of the side lobes, that means highest value of the local maxima, and ratio of main beam amplitude to that amplitude is what is called the side lobe level. So we define this characteristic parameter, what is called the side lobe level, which is nothing but the largest side lobe amplitude divided by the main lobe amplitude. Since the main lobe amplitude is for normalized radiation pattern is unity, essentially the amplitude of the largest side lobe, that defines the side lobe level. Typically this number for a good antenna may lie between about 20-30 dB. So if you take the antenna which are used for example satellite communication, this number typically would lie in about -20 -30 dB. So dB we define as we normally do, this is the ratio of the two amplitudes. So we can take 20 log of that quantity, that will define the side lobe level in dBs. So this quantity in general can be written in terms of dBs. So now we have got these parameters from the radiation pattern, like the direction of the main beam, the half power beam width of an antenna, and the two in two principal planes, the E plane and H plane, and the beam width between the first nulls and the side lobe levels for the radiation pattern. Of course, for relative comparison we can use this quantity, what is called the half power beam width, but we require still more compact parameter to represent the antennas, or we require a parameter which can define really the focusing capability of the antenna. That means if I want to design a very directional antenna, I must have a characteristic parameter to define that focusing nature of the antenna, how focusing this capability this antenna has, and that parameter is what is called the directivity of the antenna. So this is a very important parameter for an antenna, what is called the directivity, and directivity essentially tells you how much capability the antenna has in focusing a power in a particular direction. So essentially we define, before we do the calculation or define what is directivity, let us define a parameter what is called the radiation intensity from an antenna. We have seen that if you know the electric field from the radiation pattern, then we can calculate the Poynting vector. But as we go away from the antenna, since the electric field dies as 1 over r, the Poynting vector, which is proportional to square of the electric field, that will die as 1 over r square. So the Poynting vector, which gives you the power density, that means power per unit area, will go on decreasing as we go from the antenna. So this parameter is distance dependent. So we define a parameter which does not depend upon the distance, what is called radiation intensity, that is the power per unit solid angle. So instead of defining a power density, which is power per unit area, we define a parameter called the radiation intensity, which is power per unit solid angle. So we define a quantity what is called radiation intensity, which is power per unit solid angle. So if I calculate power in a given direction theta phi, then power divided by the area, that gives me the power density, and solid angle for a given area is the area divided by the r square from the antenna. So if the antenna was here, let us say I take some incremental area here, which is dA, that is the solid angle with this area subtends on the antenna. So if this distance is r, this solid angle d omega is equal to dA upon r square. So if I know the power in a particular direction theta phi, this quantity radiation intensity, let us call that as u of theta phi, that will be power in the direction theta phi divided by the solid angle d omega. I can substitute for d omega from here. So this will be the power in this cone along theta phi divided by dA into r square. But this quantity p theta phi upon dA is nothing but the Poynting vector. So that gives you the power density. So the radiation intensity is the power density which you get from Poynting vector multiplied by r square, that is the radiation intensity. So this is essentially the power density, which is the Poynting vector. So this is E theta phi square upon eta. This is a transverse electromagnetic wave. So this is actually the Poynting vector is E cross H, but E and H are perpendicular to each other and H is E by eta. So you get the Poynting vector, which is mod E square upon eta multiplied by r square. And since the fields vary as 1 over r square, essentially this r square will cancel with that. So this radiation intensity will be independent of the distance, and that is what is fine, because we have defined this power per unit solid angle, and this angle does not change as we move from the away from the antenna. This angle is same. So the total power which remains in this solid angle, that is independent of the distance. So now what we can do, once we define the radiation intensity, then we can ask, if the antenna was directional, how much radiation intensity it would produce in the direction of maximum radiation compared to if the radiation was uniformly distributed in all directions. That means if I take certain amount of power and give it to an antenna which is very directional, it will produce certain radiation intensity in the direction of maximum radiation. Suppose I had given the same power to an hypothetical antenna which would distribute power uniformly that means this antenna is an isotropic antenna, it will produce certain radiation intensity in that direction. The ratio of the two radiation intensities we call as the directivity of the antenna. So, essentially what we are saying is the directivity of an antenna is the maximum radiation intensity which you can get from the antenna divided by the average radiation intensity which you can get from the antenna, because if the antenna is treated isotropic, the same power is going to uniformly get distributed over the solid angle. So, you will get the average radiation intensity. So, we define now the power which you get here is over integrated over 4 pi solid angle, 4 pi radiation intensity u theta phi, if I integrate over solid angle, that essentially gives me the total power radiated by the antenna, because this is per unit solid angle power. If I integrate over solid angle, then I will get total power which the antenna radiates. So, this one if I write specifically in terms of spherical coordinates, this is theta equal to 0 to pi, this is phi 0 to 2 pi, the radiation intensity theta phi sin theta, this incremental solid angle d theta d phi. So, this is the power radiated by the antenna. So, if I knew the distribution of the radiation intensity, then I can find out what is the total power radiated by the antenna. And let us say I am taking the radiation pattern which is normalized. So, the maximum value of this quantity would be 1. So, then I will get normalized power essentially. And if I take the actual radiation intensity, then this will give me the total radiated power. So, what is the average radiation intensity? This is the power now which is going to get uniformly distributed in all directions, and all direction if I take the total solid angle is 4 pi. So, the average radiation intensity will be this quantity divided by 4 pi. So, I get average radiation intensity U average, that will be W divided by the total solid angle which is equal to 4 pi. So, this is nothing but 1 upon 4 pi into this quantity U theta phi d omega. Then as we said, the maximum radiation intensity which you get from the radiation pattern divided by the average radiation intensity, that is what we define as the directivity of the antenna. So, we have now the directivity let us say denoted by D, that is equal to the U maximum divided by U average. So, that is equal to 4 pi U maximum divided by U average. So, this 4 pi, this will be integral U of theta phi d omega. So, since all the constants which are involved here, since we are not interested in the absolute power calculation, this variation of U theta phi is proportional to square of the electric field. So, in fact, this quantity except the proportionality constant will be given by the square of the electric field as a function of theta and phi. That is what the Poynting vector is. So, whatever are the proportionality constant, they will get cancelled. Now, this is you are taking a ratio of these two quantities. So, I can replace this u max by square of the maximum electric field. This I can replace by square of the electric field in general theta phi direction and find out the integral over the total solid angle. So, I can write down the directivity in terms of the electric field d is equal to 4 pi mod E maximum mod E square maximum divided by solid angle mod E theta phi square sin theta d theta d phi, and this is a double integral theta equal to 0 to pi and phi equal to 0 to 2 pi. Now, the radiation pattern, so this quantity essentially you can get from the radiation pattern. So, the directivity is a parameter which is purely defined by the radiation pattern. And in fact, since again we are going to take the ratio of these quantities, even the absolute value of the electric field do not matter. So, even if we take a normalized radiation pattern with maximum electric field is equal to unity, that means E max by definition is unity, the directivity, this quantity d will not get affected, because whatever is again the constant, it will get cancelled from here. So, generally for directivity calculation, you can define what is called normalized radiation pattern, which is defined by E theta phi divided by E maximum mod E. Then by definition this quantity is unity. So, we get the directivity of an antenna which is nothing but 4 pi divided by the normalized radiation pattern. Let us call this quantity is E normalized. So, this will be this integral E normalized theta phi square sin theta d theta d phi. So, if you know the normalized radiation pattern, essentially you can calculate the directivity of a given antenna. Now, as you can see from here, essentially the directivity tells you the enhancement of the power density in a given direction with respect to an isotropic antenna. So, this quantity by definition is always greater than 1. For an isotropic antenna, this quantity will be equal to 1, but any other antenna which is directional, this quantity by definition has to be greater than 1. So, we have d which is greater than or equal to 1, where the equality sign is for isotropic antenna, and for directional antenna the directivity is always greater than 1. And higher the value of directivity, more is the focusing power of the antenna in a given direction. Our interest is to make an extremely high directional antenna, then the directivity should be as high as possible. So, this is what precisely is done when you go to the systems like satellite antennas. Those antennas have a directivity which is very high. They have directivity typically of the order of about 10 to the power 5, 10 to the power 6. So, they have a focusing power which is very high. So, the power is not wasted in other direction, the power is focused precisely in a given direction. Now, as we have done earlier, if I make now approximation to the radiation pattern as we defined here like this, and if I say that effectively the power is confined to the half power beam width, and I take two planes and let us say side lobe levels is much smaller for this antenna. So, I have let us say an antenna whose radiation pattern is typically like that. In 3 dimension it will be like this. Like that. So, I have one plane, in this plane I have radiation, the half power beam width which is something, the perpendicular plane I have half power beam width, and the side lobe levels are very small. So, practically if I see like a Cartesian coordinate system, I will have a radiation pattern which will look like that. Like this. These are 2 perpendicular planes, this plane and the other plane. Then I can visualize this like a box where the half power beam width for this is this, the half power beam width for this is this. So, I can visualize this as a box of like that, where this width is theta half power. Let us say this direction we have the angle phi. So, this is phi half power, this direction, this is theta half power. So, we can make an approximation that the power is just confined to this region of half power beam width, and beyond that the power is practically 0. So, the integral which I require for E square, essentially I can just say that this is approximated by a box which is this, and so on. And within this, since it is a normalized radiation pattern, this amplitude is 1, so that means the height of this box is unity. So, the integral which we got here, this thing, under the assumption that this angle is very small, this integral essentially is equal to the volume under this box with the height of this box equal to unity. So, essentially we get this 1 multiplied by theta half power, phi half power, that is this quantity which will be giving you this integral. So, we get now the directivity for a what is called a highly directional antenna. So, if you take very narrow beam, main beam, such that your theta half power and phi half power are much smaller compared to 1 radian, then this integral can be approximated by simply theta half power and phi half power. So, I can substitute now into this. So, directivity approximately for a highly directional antenna is 4 pi divided by theta half power, phi half power. Where these theta half power and phi half power are measured in radians, these quantities are in radians. So, if I could measure the half power beam width of an highly directional antenna, then the calculation of the directivity is approximate value of directivity is rather very straightforward. So, that is why whenever we design an antenna, if it is directional, the first attempt is to measure the half power beam width, because once you measure the half power beam width, then from there you can calculate this very important parameter which tells you the focusing capability of the antenna called the directivity. Take for a simple example, suppose I have an antenna which is having a half power beam width of 1 degree. So, let us say if I take a parabolic dish kind of antenna which gives me the half power beam width of 1 degree by 1 degree, it produces a main beam which is circular, and these both of them are let us say 1 degrees. So, as an example, just to get a feel what kind of directivities are produced, let us say theta half power and phi half power are equal to 1 degree. We want this in radians, so this is equal to u pi upon 180 radians. So the directivity for this antenna D will be 4 pi divided by pi upon 180 whole square. So this value, if I approximately, if I calculate, this will be 4 pi, this is pi square will be approximately 10. So this is, if I say this is 10 pi square multiplied by 180 square, so this will be 180 square. So approximately this would be, if I take this pi upon 180 is approximately like 60 degrees, that is what approximation we can use. So that gives me 3600 multiplied by 4 pi. So you will see the directivity of this approximately will be about 4 pi into this quantity will be about 3600. So we got here now the directivity, which is something like about 36 to 40,000. So if you take an antenna whose half power beam width about a degree, then this antenna has a focusing power of about 40,000. What that means is that at a given distance, this antenna would enhance the radiation intensity by a factor of 40,000, and that is very interesting now, and that is the reason we call this also as the gain of the antenna. That is, if whatever power you had, if you had just thrown away the power uniformly in all directions, you would have got certain amount of power there. Now this antenna is going to enhance the power by a factor of 40,000. Said differently, if I did not have this antenna and I wanted to produce this power density at a given distance, I will require the power which is 40,000 times more than what now I can handle with this antenna. So let us take a typical example. Suppose I wanted to have a certain radiation intensity which I would have got this with this antenna. But this, and let us say that power which I required was about 1 watt for this antenna. So I take this antenna, I supply 1 watt of power to that antenna, I get certain radiation intensity at a certain distance. If I did not use this antenna, and if I use an antenna as like an isotropic antenna, then I will require 40,000 watts of power to get the same radiation intensity in that direction. Imagine a situation that let us say we want to establish a communication between satellite and ground. If this antenna was not there, the power requirement will go from tens of thousands to million. So whatever communication today we are achieving with few watts of power, that would need few megawatts of power. So the antenna which looks the most passive element in the entire communication system, in fact is really the heart of the communication system, because if this antenna was not there, the power requirement of the communication link will increase by such an order that we will not be able to realize those kind of powers. So it is very important that when we talk about the point-to-point communication like microwave link or satellite communication, we use the antennas which are highly directive. That means their directivity is very, very large. By doing this, essentially we are reducing the power requirement capabilities of the communication link. So the antenna essentially provides the gain in the power in certain direction. Of course, this gain is not in the conventional sense like amplifier, where the power is amplified, the antenna is that way is a passive device. So, you are supplying certain amount of power to the antenna. What then gain tells you is that the power is enhanced in a given direction, of course at the cost of other directions, but in those directions we are not interested in. So, this gives you enhancement of the power or amplification of the power in a given direction. So, this is not the increase in total power which is radiated, the total power which is radiated is conserved, it is same. Only thing is, by antenna the power is redistributed and it is enhanced in a certain direction. So, in that sense, for that particular direction we can say that there is an amplification of power compared to if the antenna was not there. So, the directivity is very important parameters, and this plays a very important role in reducing the power requirement in the communication link. These are the certain important characteristics of an antenna when the antenna is used as a transmitting antenna. In the next lecture when we meet, essentially we will try to look at the antenna like a receiving antenna, that if the antenna is kept in the electromagnetic field, how much power it will receive from the electromagnetic field. So, antenna, as we saw, is a device which is a transducer which converts the electric and magnetic fields to voltage and current and vice versa. We saw one aspect, converting current to fields. In the next lecture we will see conversion of the fields to the electrical quantities like voltages and currents.